Alright guys, this right here is to explain number 43, which a lot of you have had problems with. What it basically describes is a charged plastic ball that's sitting in between the two plates of a parallel plate capacitor. And the ball is held by a string. If you want to draw it, it is held up at an angle of 30 degrees. You can assume that the electric field is going across this way. Let me actually change the color of this way. And the first step is going to be to draw a free body diagram on this ball. So we have tension going up here at the 30-degree angle. We have gravity going down. And you're told that the charge of the ball is going to be plus 0.15 times 10 to the negative 6 coulombs. Since that's a positive charges go with the field, so you can assume the electrical force is acting to the right here. Called that F sub E. And the ball is at equilibrium, which means it's not moving. So ups equal downs, lefts equal rights. So once you have this free body diagram, I'll redraw it right quick. The first step is going to be to split your tension into its two components, those being the horizontal and the vertical, or we call that Tx. This is Ty, and to go ahead and assign those values in terms of your tension with your angle. So your horizontal component is going to be T sine 30, and your vertical component will be T cosine 30. Now, since you know this is an equilibrium, then your T cosine 30, your vertical component here, is going to equal your force of gravity, and your T sine 30, your horizontal component, will equal your electric field force going to the left. Now the first thing to do is to solve for your force of gravity, because we know what the mass of the ball is. So the mass of the ball is 6.50 times 10 to the negative third kilograms. If we multiply that by 9.8 meters per second squared, that'll give us the force due to gravity. Let me pull the calculator right quick. And that's going to be, it's going to be 0.0065 times 9.8. It's going to be, this force of gravity will be 0.0637 newtons, which means that my T cosine 30 up here will also be equal to 0.0637 newtons. So if I divide each side by my cosine 30, I'll find that my tension is equal to, divided by cosine 30. Phone calculators are always aggravating. So cosine 30 is 0.866. So we want to say 0.0637 divided by 0.866 is going to be 0.0736 newtons. Now that's my tension. Now if you go look at your horizontal sides, you have that your electric field force is going to be equal to T sine 30. So what I'll do is take this tension that I found earlier and plug it in for my T. And that gives me that my electric field force is equal to 0.0736 times the sine of 30. Sine of 30 is 0.5. So that gives me that my electric field force is 0.0368 newtons. Now, you know the electric field force is caused by the interaction of a charged particle within an electric field. So the formula for that is that the electric field force is equal to the charge of the charged object, Q, times the electric field itself. And this electric field itself is what we need to determine what the charge on the plate of the capacitor is, which is what you're asked for in this problem. The charge on the plate determines the electric field, and that electric field determines the force that this charged particle is experiencing. So if I plug in my value 0.0368 newtons, and I know the charge of my object, which is 0.15 times 10 to the negative 6 coulombs, that's 0.15 microcoulombs, times my E, I I can get my electric field force. Give me just a second to pull this up. So that's going to be 0.0368 divided by 0.02345615, which is going to be an electric field force of 245,333.3 newtons per coulomb. So keep that number in mind, because we're going to need it in just a minute. Now, if you go and look at the formulas we did in class today, we did 3 formulas that really talk about electric fields in parallel plate capacitors. The first one being that the electric field that is created between 2 metal plates, or 2 parallel plates, is equal to the voltage over the plates divided by the distance between the 2 plates. The second formula is that the capacitance of a parallel plate capacitor is equal to the charge that is held on the plates divided by the voltage across those plates. And the third formula was that the capacitance in a parallel plate capacitor is equal to epsilon naught, that being the free space permittivity, times the area between the 2 plates and the distance the 2 plates are held apart. So what we need to do is combine all 3 of these formulas together to create another formula that can tell us what Q is, while also using the electric field force and the area, because those are the 3 things that were given in the problem, or that we really know. We're asked to find Q, A is given to us, and E we just determined a minute ago. So I would start with this first formula here. So if E equals the voltage between the plates over the distance, I can rearrange this for voltage, because I know that voltage exists at another spot in this equation. And if I rearrange this for voltage, I can take this first equation, plug it in the second equation, and make a combined equation, basically. So if I solve for my voltage, I can multiply each side by D, and I get that voltage equals my electric field times the distance between the 2 plates. Now, if you take this second equation here, C equals Q over V, we plug in this new part with it, we get that the capacitance is equal to the charge on the plates of the capacitor, the thing that we're looking for in this problem. So we're looking for, that'd be the capacitance equals Q over my voltage, which is now electric field times distance. Now, we can then use our third equation, which is this epsilon naught A over D, which equals C, instead of equal to this second equation we just developed, because they're both equal to the capacitance of a parallel plate capacitor. So that tells me that epsilon naught A over D, my third equation I did earlier, is going to be equal to that new equation I just created, which is Q over ED. Now, first thing is to see you have D on the denominator on both sides, so it automatically cancels out. Which gives us that epsilon naught A equals Q over E. Now, if I multiply each side by E, they cancel out there, giving me a new equation for my charge, which is epsilon naught A E. Now, epsilon naught is the free space permittivity. That is a constant that we already know, which is 8.85 times 10 to the negative 12 coulomb squared per newton meter squared. The area is given to us in the problem as 0.015 meter squared, and the electric field is the 245,333 newtons per coulomb we just determined. So let's take and plug those in. Here's our formula. We know Q, or we're looking for Q, excuse me. We know epsilon naught, which is 8.85 times 10 to the negative 12th Newton. That is not newtons, that should be coulombs. Coulomb squared per newton meter squared. Units are not all that important on this epsilon naught. They'll be later, but not for today. The area is 0.015 meters squared. And that electric field is going to be 245,333.3 newtons per coulomb. Put that down there and draw a little arrow right here because I ran out of space. And if I multiply all this together, I get my charge. Now, 8.85 times 10 to the negative 12. It's not negative 12. Well, if I plug all this together, what I will get is Q equals 3.25 or 3.26, depending on your significant figures. Let's call it 3.25 times 10 to the 8th, negative 8th, excuse me, coulombs. Now, if you really want to determine how many electrons or protons are on this, you could then divide this Q by the charge of a proton, and you can see how many protons are on each plate. But for this problem, the D2L problem is only asking for what the Q is, so the charge is 3.25 times 10 to the 8 coulombs, and that's it.